Are able to see my slide? Let us wait for others to join. Anyway, let's get started. Good evening, everyone. Welcome to the week 6 live session of Digital Design with Verilog. First, let me introduce myself for the students, those who are joining for the first time. My name is Bijin Elsa. I'm a research scholar from Mehta Family School of Data Science and AI, IIT Palakkad. And I will quickly go through the logistics of the live session. Every week we have live session on Sunday from 6 to 8 p.m. It's a 2-hour session. In this live session, we will have a recap, a quick review of the previous week course content, and we will also have problem solving session. In the session, we will mainly focus on the problems which are similar to your assignments, not the exactly same questions. similar question. And time will be provided to solve each problem, and you can post your response in the chat box. If you have any doubts from the previous week content, or if you want me to solve any problem, you can also post your queries in the chat box and ask me at the end of the live session. After the live session, we will provide the recording and the slides you can access through a sheet shared by the NPTEL. The sheet will be available in the course webpage. So this is the syllabus of the course. The first half mainly about the switching algebra, different number systems, and how we can simplify the Boolean expression, and the combinational logic block, and we will start the Verilog. So this week we are going to design few combinational logic block, and we will also see how we can design the combinational logic block using the Verilog. And the second half is mainly about the sequential circuit. It's about the flip-flops, state machines, registers, counters. And at the end of the course, you will also have a basics of the FPGA architecture. So this week we are going to start with the combinational circuit. First of all, what is combinational circuit? It is a circuit where the output depends only on the present combination of the inputs at that point of time. Suppose this is a combinational logic circuit with n inputs and m outputs. When you have n inputs, you will have 2 raised to n possible combinations. And output, we can express the output using the input variables by a Boolean expression. For example, y1. This is using the OR gates, and this is using the NOR gate. Now let's look into the design procedure for the combinational circuit. The first step is that you will have the design specification. From this specification, you have to determine the input and the output variables. Second step is that construct the truth table, which should define the relationship between the input and the output. Then from the truth table, we can obtain the simplified Boolean expression. Then finally, you can draw the logic diagram. And you can write the Verilog code and verify it through simulation. So these are the main important steps you need to consider while designing the combinational circuit. Now let's design a circuit BCD to XS3. It's a chord converter. So the design specification, we have to design a chord converter that should convert the BCD to XS3 chord. So BCD, we can represent the numbers from 0 to 9. So first step is that determining the input and the output variable. So input should be a 4-bit and XS3. So output also a 4-bit. Now we can construct the truth table. This is a 4-bit, so you will have 16 combinations. XS3, add 3. All of you fill the remaining combination and find out the simplified expression for Z, Y, X, and W. Use the K-map to get the expression. You can post your answers in the chat box. And 10 to 15 for other combinations, it will be down kills. All of you got the Boolean expression for set y x w. So this is the truth table. So using K-map, you can find expression for z, y, x, and w. So what is the value? What is the expression of z? Has anyone got the expression? Post your answer in the chat box. 0357 03578. Are you talking about the expression of Z? I will show you how to solve for one variable. Or Z 0, 4, 6, 8. 0, 6, 8. From 9 to 15, it's don't care. Now tell me what is the expression of Z. For Z, it was 0, 2, 4, 6, 8. These are the midterms. Now you have to simplify the expression using the K-map. Has anyone got the expression? Set this D bar. So you can group this for total. It's a group of 8 octet. So you will get the expression Z equal to D bar. Similarly, find out for Y, X, and W. A plus BC. One more term is there. Total 3 terms are there for W. Anybody got the expression for the other 3? Here Y 0, 3, 4, 7, 8. Zero, 4, 7. It's 1, 3, 9. W 5, 6, 7, 8. Did you all got the expression? Just group it and find out the expression now. This is not X, okay? This is don't care. This is don't care, okay? This is not X, it's don't care. For BCD, BCD is binary coded decimal. We'll have values from 0 to 9. Right, 0 to 9. For the other combinations, it will be don't case. This is a for bit. So for other combinations, it will be don't care. Don't confuse with this input X and this one. So 10, 11, 12, 13, 14, 15, for all those input combinations, it will be don't care. What is the expression of Y? We can group for each. So what will be the expression of Y? Post your answers in the chat box. Even if it is wrong, that is fine. Yeah. C bar, D bar plus CD. And what about X? So we can group this for ones together for midterms, and here we can group for midterms. So here, how you will find out C bar, D bar, and CD? That is like 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0. So this will get cancelled. You will get C bar. This will be A, B, C, D, right? Similarly, you can find out for this group. You will get CD. Is that clear? For this group, you will get CD. Yeah, B, C bar, B bar, S, This one be C bar D bar. B bar C, not BC. Plus B bar D. W. This one we can simplify further. B C bar D. We can take B bar common. C plus D. This C bar D bar, we can write it like this: C plus D the whole bar. This is based on the De Morgan's law. D bar C plus D. Is this clear how we got this final expression for X? And for W, this one. What is the expression of W? Anybody got the answer? Yeah. A plus B, B plus BC. So from here we can take B common, right? B, C plus D. Have you all solved it till this point? Is there any doubt? So we have completed till the third step. Now we are going to draw the logic diagram. And based on this equation, we can write the Verilog code as well. So these are the equations. Z equal to D bar. And Z equal to D bar, right? Y equal to C bar, D bar plus CD is equal to C plus D plus B, C plus D, without W equal to A plus B, C plus D. This is don't care. Okay. So BCD binary coded decimal we can represent only from 0 to 10. But this is a 4-bit, right? 4-bit input. So for the rest of the combinations will be don't care. The output will be don't case. So we can use this don't case to group with other minterms so that we can simplify the logic expression. This is not X, okay? This is don't case. Oh, okay, okay. You want me to explain this one? This X came up. This one, we can group this for. So when you group this for, you will get B bar C. Then when you group this, you will get B bar D. Okay. Then when you group this two, you will get B, C bar, D bar. Now from this, we can take B bar common. So when you take B bar common, it will be like this, B bar C plus D. Then here we have a minterm that is B C bar D bar. Using De Morgan's law, we can write it C plus D the whole bar. Okay. Now you can draw the logic diagram. Set this D bar, right? So this is D bar. So this will be the set first output. Then next is C bar D bar plus CD. Okay. This one, using the De Morgan's law, we can write it like C plus D the whole bar. We can write it like this, right? So CD is already here. Now we have to take C plus D the whole bar. So this is CD, this one C plus D, C plus D, the whole one. So this will be 5. Now X. Here C plus D bar and D D bar C plus D. This will be X. This is B bar C plus D. This is C plus D. Now A and W, B, C plus D. So this is W, X, Y, Z. These are the output and these are the input. A, B. This is C, A, B, C, D. So this is how you can draw the logic diagram from the expression. Now I'll show you how you can implement using the Verilog. So you have to create a module name. You need to write BCD to XS3. Then you have to declare the input and the output ports. Input A, B, C, D, then output Z, W, X, Y. Using data flow modeling, you can simply write using the expression. So the first one is set, assign, set. It was D complement. So not of D, assign. Next one was Y. It was CD plus C complement D complement. So C and operator. This is a bitwise operator you have to use. Then OR, not of C and operator, not of. Similarly, assign X, the equation will be not of B and C or not of B and D or B and of C and not of D. So what will be the equation for W? This is simple, right? So from this expression, using the bitwise operator, you can write it. This is the data flow modeling. So how you can write for W? What was the expression? It was A plus B into C plus D. Or you can just multiply this B and C plus B and D. That is A or B and C or B and D. Then you have to write end node. So you can write a test bench for this code and give the different input combination, and you can verify how the output will be. If time is there, I will show you how you can run it in the EDA platform. Is that clear? Any questions? This is data flow model. Okay, next we will design another combinational circuit, that is a parity bit generator. 3-bit. Okay, 3-bit parity bit. The 3-bit parity bit generator, even parity bit generator, then output will be 1 if uh, if it has odd number of ones in the input bits. So this is a 3-bit. Okay. Now construct the truth table. EDA platform, EDA playground. It is available online. You can check it. EDA playground, where you can simulate the code. Do I need to show you again? So EDA playground, here you can implement your design, and this is the test bench. Test bench here, Here you have to declare the inputs and outputs. And this is a module instantiation where you have to map the inputs from your test bench. Then this is clock and reset. Initial value, initial clock will run only at once. It will start at the simulation time 0. So initially the clock value is 0 and reset is 1. You will have a delay of 20 nanoseconds. This is the time scale. Okay, this is in nanosecond only. You have to declare the time scale. Here it is. I didn't write it here, but you have to write the time scale here. And this always here. So after every 10 nanosecond, the clock is going to change the value. It is going to take the complement of the value. So after 10 nanosecond, this is going to become 1. So this is the always, it will run continuously. Then this is like at every pause edge of the clock, we are giving one input combination. So BCD, it is from 0 to 9. When it becomes 10, it will stop the execution. Here on the website, you can select the simulator and test bench system Verilog or Verilog you need to select. And you can run it. Has anybody used ADA Playground before? If you want to see the waveform, you have to give then you have to select opening wave after run. So here you can see an A, B, C, D. That time what will be the value of W, X, Y, and Z? You have to give one here. Then you don't have to add the waves manually. It will automatically shown in the waveform window. This is in order to see the waveform, you have to capture all the input and the output. That's why we are using this dump file and dump parse. You need to write this two lines, then only you can see the waveform. You need to select the option as well. You can also download the output file. If you give, you can give some name and you can also download the output after running the code. Your download option is there, show output file after run. So you can explore this online platform. Now let's come back to the parity bit generator. All of you construct the truth table. So XY set output. This is the input, this is the output. So if it has odd number of ones in the input bits, then you have to give 1. If it is even number, then you have to give 0. Then using K-map, find out the expression for P. So here it is 0, 0, 0, 0, 1. Now the K-map. What will be the expression of Here you can group individually, cannot group two bits and all. It's not possible here. So the expression will be x bar y bar z as x bar y z bar x y bar z bar plus x y z. Using this expression, you can draw the logic diagram. I'm not going to draw. You can try the diagram later. So how will be the Verilog implementation? I'll show only the uh, expression, same P. Okay, this equation we can simplify. Instead of writing such a long expression, we can simplify this expression. Here, we can take x bar common, right? Y bar z plus y z bar as here we can take x. This is y bar z bar plus yz. This is XOR and this is XNOR. So x bar y bar z plus yz bar as x. This one we can write it like this, right? Y bar z plus yz bar complement. So that will be like x bar I XOR z as x I XOR z all complement. So this is also XOR gate, right? Like A bar B plus AB bar. So we can write it like XOR I XOR Z. The logic diagram will be like X, Y, Z. X XOR Y XOR Z. And in the Verilog, I'm not writing all the module definitions and input put. The final will be same P XOR XOR Z. Is this clear? And the next one is the comparator. So comparator is going to compare the magnitudes of two numbers or compare x, y. This is 2-bit, okay? So these are the different output functions f1, f2, f. F1 will become 1 if x is greater than y. F2 will become 1 if x equal to y. F3 will become 1 if x less than y. So you can construct the truth table x1, x2, y1, y2, So you will have the 16 combination 0, 0, 0, 1, 0, 0, 1. Like that, you will have till 1, 1. So F1, F2, F3. This is same, right? X1, X2, Y1, Y2. All the bits are same. So F2 will be 1, F1 and F3, 0. This one here, this is highest, Y. X less than Y. So 0, 0. So similarly, you have to construct the truth table. And you need to find out the simplified Boolean expression for F1, F2, and F3. This is a 2-bit comparison. All of you understood till now? Any questions? So if it is a 4-bit comparator, this is 4-bit. So A is 0, B3, B2, B1, B0. So it is like it will be a big truth table if you write all the combinations and find out the parity. So instead of that, we can get the simplified equation using a easy way. So we have to check A greater than B, A equal to B, or A less than B. First, we will consider A equal to B. When will A equal to B? If all the bits are same, then it will become A equal to B, right? So we can represent it in like A equal to B, X3, X2, X1, X0. So when A3 and B3 becomes same, that will be X0. We are representing A0 and B0, X0, A1, B1, X1, A2, B2, X2, A3, B3, X3. So when you take the AND operation, it will give, if all the values, okay, before that I will tell you what will be the xi, okay. So if the bits are same, if we use the XNOR gate, if the bits are same, it is going to give 1. That is AI of BI as AI complement BI complement. So here for XOR, how the truth table is, if all the bits are same, it is going to give 1. So what we are going to check, we are going to check A0, B0, A1, B1, A2, B2, A3, B3. So if both the bits are same, this is going to give 1. Then we are taking the AND operation. If all 4 bits are same, then it will be going to give 1. So this is the expression for the comparing whether A equal to B. Now we need to find out the expression for A greater than B. So we have A3, A2, A1, A0, B3, B2, B1, B0. So you have to start from the MSB. If A3 is 1 and B3 is 0, A is greater than B, right? This will be 8, or the number will be greater than 8. This will be, the number will be less than 4. So we can write A3, B3 complement plus next one, again the same, A2, A2 is 1 and B2 is 0. A is greater than B2. But here there are two combinations, right? A3 can be 1 or A3 can be 0. Here B3 can be 1 or B3 can be 0. So you have to take x3. What will be the value of x3? So what is x3? x3 will be, you need to do the XNOR operation with A3 and 3. So if it is same, this is going to return 1. If it is different, that is going to give you 0. So x3, A2, 2 comp. And next one we need to check, that will be A1, B1 complement, and we have to check the other two positions also. So x3, x2. Next one, A0, A0 complement, x3, x2, x1. When A less than B, it will be opposite. So that time A3 complement B3. So here A3 will be 0 and 1. That time it will be A less than B. Say x3, A2 complement B2 as x3, x2, A2, sorry, A1, 1, A1 complement B1, x3, x2, x1, A0 complement 0. So this will be the simplified expression for the 4-bit magnitude. If you are going to construct the truth table, that will be very big and it will be a tedious job. So this is how you can find out the simplified expression for the 4-bit comparator. Now moving to the next combinational circuit, MUX. Multiplexer, that is, it is like a switch that is going to connect one of the n inputs to the output. So you will have select lines, input and output. So if you have two select lines, then input will be 2 raised to n minus 1. Input from it will be from 0 to 2 raised to n minus 1. This is an example. So in it, so this will be 0 this is raised to n and output will be 1. So you have select lines, 0 and S1. When you have two select lines, you will have 4 input lines. So this will be like 2 raised to n into 1. That is 4 cross 1. This is the output. And this will be the input. 0, I. The truth table, how you can construct the truth table is 0 is 1. This is the input. This is the output. When select line becomes 0, 0, it will pass the input I0 to the output. Then when select line becomes 0, 1, this is going to pass I1. 1, 0, I2, 1, 1, I3. You can draw the logic diagram and how the Verilog implementation. So it will be using the data flow modeling as saying I 1, 2, S1, S0, input will be I0 or S1, S0, S1, not of S0, S1, S0. You can find all the Verilog codes in the course webpage and you can try it on the PDF lab. And using maps, we can also implement certain switching functions with multiplexer. So like how you can implement XOR using 2 cross 1 maps. 2 cross 1, how many select lines are there? Two cross 1. So it will be 2 raised to n into 1. So what will be the value of n? N number of select lines. So how many select lines? For 2 cross 1 marks, how many select lines will be there? 2. If it is 2, then how many inputs? 2 raised to n, right? This is 2 cross 1. 2 raised to n cross 1. That is 2 cross 1. So n is 1. If it is 2, then it will be 4 cross 1. And 4 cross 1. For 2 cross 1, you have only one select line. Now we are going to implement the XOR, right? XOR, how the output is, suppose you have two inputs A bar B plus A B bar. So this is the output, and select line, we are giving input A to the select line. Okay. So when A becomes 0, that is when A become A bar, it has to pass. This is the input I0. I1. When A becomes 1, it has to pass A bar. So F will be equal to A bar B plus A. Is that clear? For a 2 cross 1 multiplexer, you have two inputs, one output, one select line. Okay. If I am giving select line S and giving I0, I1. When S equal to 0, this is going to pass I0. When S becomes 1, this is going to pass I1. Okay. Now we want to implement XOR using 2 cross 1, right? So the final equation for this will be S bar I0 plus S I1. When S becomes 0, that is S bar. This is going to pass I0. Then when S becomes 1, this is going to pass I1. So this is the expression for the mux. Now we are going to implement XOR A bar B plus A B bar. We are giving A to the select line. When A becomes 0, that means when it becomes A bar, it has to pass B. So the one input is B. When A becomes 1, it has to pass B bar. So this will become A bar B plus A. Is that clear? Is that clear? Since the demultiplexer, so here you will have one input, two raised to n output lines and n select lines. So if n equal to 2, then you will have 4 output. So this will be 1 cross for Emacs. What is Emacs is going to do? This is going to direct input to any of this output based on the select lines. Time is running, so I'm not going to show you the truth table and logic diagram. So moving to the next circuit, that is encoder. So encoder will have 2 raised to n input lines and n output lines. It will be like suppose n is 3, then it will be those 3 encoder. This will be the output. And the first input is 1, then it is going to generate a binary code 000. And second, this is going to generate 001. Third, 010. Similarly, till 11. So here one limitation is only one input can be active at a time. So only one input is active at a time. If two inputs are active simultaneously, then this is going to generate an undefined output. And there is something called priority encoder, where you will be giving priority to certain inputs. So in priority encoder, it will be like so this is going to produce the binary output code. It will indicate which of the input lines requesting services has the highest priority. So for this one, this will have the priority, and so similarly will be using the truth table. You can find out the value for x, y, z, and you can also try the Verilog implementation. And the next one is the decoder. Decoder, it will have n inputs and raised to n outputs. One is one of the application is decoding the memory address, and here you have suppose 3 inputs, then you will have 8 outputs. So for the binary combination, you will have the exact opposite of encoder 000. Then D0 to D7, you will have 1 0 0 0 0 then 0 1. Similarly, you will have till 1 1. And there is one more important thing which I want to tell, that is a decimal decoder. So this one is a binary decoder. For decimal decoder, this is going to represent only from 0 to 9. So it will not have 10 to. So this for decimal decoder, it has less number of logic gates than the binary decoder. And we can also implement the switching function using the decoder as well. Just you need to include one OR gate at the end of the output. And demux is also a decoder with one data input and n address inputs. Demux usually 1 cross 4, right? It will have 2 So this is like n cross 2 n, right? Decoder. So the demux, we can say this is one data input and 2 input lines and 4 output. So demux is also a decoder with one data input and n address input, so n select lines. Okay, now quickly we'll move to the questions. The first question, we want to design a combinational circuit that takes as input two 2-bit binary numbers x and y. X and y, it's a 2-bit binary number and it will outputs 1 if x greater than y. Choose the minimum number of and or gates required to design the circuit, assuming we are provided only 2 input or gates and 2 and 3 input and gates. So this is a comparator and needs to compare only x greater than y. It's a 2-bit comparator. So which is the correct option? Are you able to see the slides now? Okay, option B. We constructed the truth table. You can find out the equation and draw the diagram. Its answer is B, 2 OR gates and 2 AND gates. The next question is, consider the statements S1 and S2 given below. The statement 1 is, we can implement the circuit in question 1 using only 2x1 multiplexer. We cannot implement an XOR gate using 2x1 multiplexer. Select the correct option. The statements, first we can implement the circuit in question 1, that is the comparator, right? Using only 2 to 1 multiplexer. Comparator A greater than B. That is, we have the expression using the OR gates and AND gates. And we cannot implement an XOR gate using 2x1 multiplexer. So which is the correct option here? We can implement that switching function using 2x1 multiplexer. I have shown one example. Similarly, we can implement the previous expression also using 2x1 multiplexer. But we cannot. The second statement is false. Okay, we can implement XOR using 2x1 multiplexer. So option C is the right answer. Is that clear? S2 is 2. We cannot implement an XOR gate using. We can implement, right? I have shown the example. This is statement 2 is false. Statement 1 is true. So option C is the right answer. Is that clear? We are able to implement the switching function XOR. Next question. Here, we want to construct a combinational circuit whose function is f. These are the minterms, okay, 1, 2, 3, 6, using a 4 cross 1 multiplexer. We consider the numbers 1, 2, 3, 6 as 3-bit binary input. So this is a 3-bit binary input, okay? We consider X and Y to be select lines. So X and Y, the inputs X and Y, you have to take it as select lines, okay? Refer to the figure below. What should be the values of I0, I1, I2, and I3? That are the inputs to the multiplex. So here S1, S0, that will be X and Y. And the function 1, 2, 3, 6. The minterms are given, okay, 1, 2, 3, 6. For this minterms, the output will be 1. So draw the truth table and tell me what are the inputs of I0, I1, and I2, I3. Excuse me. So here the minterms is F6, X, Y, one, 2, 3, 6. The rest of 0. So this is, you can draw the, so here will be X bar, Y bar, X bar, Y set, X bar, Y set bar, this one, X bar, Y set, X, Y set bar. Correct, right? Now we have marks, select lines are X and Y. You have 4 inputs, right? So X, Y, when X and Y becomes 0, 0, it will be set. Then X bar Y, that is 0, 1. Then it will be set 1. Sorry, set dash. Okay, here there are 2 X bar Y. Okay, then here it will be X bar Y set bar set. That will be 1. This will be 1, right? So 1. The next one, 1, 0. That is xy bar. It is not there. Xy bar. That will be 0. Then xy set bar. So these are the inputs. Set 1, 0, set bar. Is that clear? Okay. So here, in terms are given. This is a 3-bit circuit. You have to write all the combinations and minterms. For the minterms, the output is 1. So 1, 2, 3, 6. Okay. Now, we are going to implement this function using the 4 cross 1. Okay. You have 2 select lines. In the question, it is given A and B is taking as select lines. Okay. And you have 4 inputs. Okay. Now we have to find out what is the value for I0, I1, I2, and I3. Okay. Then this is the minterm, right? X bar, Y bar, Z. X bar, Y bar, Z. This one, X bar, Y, Z bar. X bar, Y, Z. And this one is X, Y, Z bar. Okay. Sorry, this is X and Y. So when X and Y becomes 0, that is, we can write it like X bar, Y bar, right? Similarly, X bar Y 0, 1. This is like 0, 0, 0, 1. X Y bar X Y 1, 0, 1, 1. Here the minterm is X Y bar Z. So when you are giving and this X and Y becomes 0, it should be Z. Then only we will get this term X bar Y bar Z. For the next term, here X bar Y, there are 2 terms, right? When X becomes 0 and Y becomes 1, there are 2. That is Z bar Z, right? Here Z bar Z. Z bar plus Z, that will be equal to 1. Here it will be Z bar. And 1, 0, that is X Y bar. X Y bar, here if you see X Y bar anything, if you take X Y bar, it is 0, right? It will be 0. It is not there in the minterms, okay? And XY, here you have XY. So when you are giving Z bar as input, then only you will get that term. Z bar. Here for the first one, it is Z. I have wrongly written this one Z. So Z is the I0, 1, I1, 0, I2, I3 is Z bar. Is that clear? Now the next question, consider the diagram below. This is a design of decoder. Here you have 3 inputs and 8 outputs. That is n cross 2 raised to n. This is a decoder. Option B. Then the next question, consider the following statement on the usage of decoders in digital technology. Decoders cannot be used for demultiplexing. Decoders can be used to decode memory addresses. Yeah, option B is the right answer. DMUX is a one input data decoder. So we cannot say that decoders cannot be used for demultiplexing. And we can use decoders to decode the memory addresses. So option B is the right answer. The next question, how many 3 cross 8 decoders do you need to construct a 4 cross 16 decoder? The answer is 2. You need only 3 cross 8 decoders to construct the 4 cross 16 decoder. So you have it 8 decoder, 3 cross 8. Suppose if it is a 3 cross 8, then yeah, XYZ and 0, 0, 0. You will have will have 8 inputs, right? So it will start from 100 7, right? Suppose if you have one more bit here, so till 111, this W will be 0. Okay, from 0 to 7. After that, from 8 to T, this will be 1, right? So from D8 to D15, you will have 0, 0. Okay, and you extend. So you can give the same input here, and you will have one enable. Okay, enable will be W. So when the W becomes 0, this is going to enable this decoder, and it is going to give the values from 0 to 7. And when W becomes 1, this is going to enable this decoder, and this is going to give the values from 8 to 15. So you will have 8 output lines here, you will have 8 output lines here. So you need only 2 prerequisite decoders to construct the 4 core 16 decoder. Is that clear? So coming to the last question, consider the two statements below. Statement 1 is a decimal decoder can be implemented with a less number of gates than a binary decoder of the same size of input. Second statement, a decoder can implement any switching function. So which of the following statements are correct? Option B. Statement 1 is true and statement 2 is also true. Decimal decoder, we will have values from 0 to 9. So we will not have from 0 to 15. So you will have less number of gates to implement decimal decoder than the binary decoder. So the first statement is true and second statement is also true. Is that clear? So with this, we are coming to the end of the session. Do you have any other questions? I'm not like it is Saturday live class is taken by another research scholar. Maybe you can drop a mail. Anyway, recordings will be available. Okay, if you don't have any questions, then we can wind up. Thank you.